In this video, we're going to talk about additive cosets of an ideal because that's the main mathematical structure we need to think about in order to construct the quotient ring of a ring by an ideal. So just as a reminder, recall if R is a ring, and we're assuming it's commutative with unity, and I is a subset of R, then I is an ideal. We can also write that I triangle R if I is an additive subgroup of R that absorbs multiplication. And by that we mean absorbs multiplication by any element of R. Alright, so in this video we're going to talk about constructing additive cosets of I. Because once we do that, this is going to give us a way to take a ring, and I'm just drawing a little cartoon here. So let's say this is R, and let's suppose that R has lots of different elements. I'm going to represent these by little dots. So each dot represents an element of R. Okay, this will take a minute here, but well, you get the idea. There's a lot of elements in R, probably hundreds. Maybe there's infinitely many, but it'd be hard to draw that many dots. Okay, what we're going to do here is we're going to separate these into additive cosets of an ideal. So there are some elements over here which belong to the ideal itself. We'll call those the subset I. So I is an ideal. And then the other cosets, they're going to be other subsets of R. And I should be drawing these so that each dot lives in exactly one coset. I'm probably not doing such a great job of that, just kind of being sloppy with the picture. But each of these cosets is disjoint from all the others, and the cosets altogether, their union is the entire ring. Once we've done that, we're going to think of each coset as being just one object. So this is one object, I, and then this is another object, and then here's another one, here's another one, here's another one, and another, nearly done, and another, and another. And then once we've done that, we have a new ring. The ring consists of all of these cosets. And we will have an operation, actually two operations, addition and multiplication, that operate on these cosets. So once we've done that, this creates a new ring which will be called R mod I. That's called a quotient ring. But before we get there, we have to talk about how we construct these sets, why they make up R, why they're disjoint, and why we can operate on them as though they're individual objects. So first of all, here's a definition. So let's let R be a ring, and I an ideal of R. Okay? Then the coset A plus I, where A is an element of R, is defined by A plus I equals the set of all A plus X such that X belongs to the ideal. Okay, so in other words, it's the set of all ring elements that can be written as A plus some element of the ideal. All right, and I'm going to make two claims about this. First of all, these cosets, they make up all of the ring. In other words, the union over all A and R of the coset A plus I, that union is the entire ring. And we're going to find that's not too hard to prove. Number two, cosets are either exactly the same or disjoint. Now you may remember a result like this from group theory if you took modern abstract algebra the first semester. This result that if we take a group and then we take a normal subgroup and form its cosets, then those cosets make up the entire group, and any two cosets are either the same or disjoint. That result holds here because R is an additive group. We are taking an additive subgroup. It is a normal subgroup because R is commutative under addition. and we're just looking at additive cosets. So you can actually carry over the group theoretic result here. I'm going to prove it just so that we have all of this in our minds as we think about these, but really this is just a result of something that you probably have already proven in a previous algebra course. All right, so first of all, let's prove number 1. All right, so this one I said would not be too hard. Here's the idea of the proof. If you want to show that every element of R is in one of these, like let's call that element, let's say you're thinking of an element B, and you want to show that B is in one of these cosets. Well, okay, just take the coset B plus I. That will contain B. Okay, so here's the idea. Let B belong to R. Then we know that the coset B plus I contains B, since we can always write B as B plus 0, and 0 has to be an element of the ideal, because the ideal as a subgroup has to contain the additive identity. Okay, so that's it. So this union contains everything in R, and because it's made of elements of R, it can't contain anything that's not in R. So this union is all of R. Okay, great. So that's number 1. Number 2, a little bit trickier technically. All right, so let's suppose A and B both belong to R, and consider the cosets A plus I and B plus I. All right, the way I'm going to approach this is I'm going to assume that they are not disjoint. So I'm going to assume that they're not disjoint and show that they have to be the same. Okay, so in other words, we're going to assume that they have some intersection and prove that that intersection forces them to be exactly the same. Okay, so I'm just going to come over here and work. So assume A plus I and B plus I have an element in common. And for lack of a better idea, let's call it C. All right, so then C is equal to A plus x1 for some x1 in the ideal, and C is also equal to B plus x2 for some x2 in the ideal. That's what it means to be in this coset, is that if C belongs to this, then C is expressible as A plus some ideal element, we're calling it x1. C is expressible as B plus some ideal element, which we're calling x2. All right, so to show that these two cosets are exactly the same, well, we'll start by showing that A plus I is a subset of B plus I. And I claim that the other argument, that B plus I is a subset of A plus I, is exactly the same reasoning. Okay, so suppose, and I'm just going alphabetically here, let's suppose that D belongs to A plus I. Okay, I'm going to move down here so I got a little bit more room. All right, so then D is equal to A plus Y for some Y in the ideal. Okay, but does that put D in any relation with B that we can state? Well, I think it does, because if D is equal to A plus Y, then we can express D in terms of C, which is linked to this other ideal here. Okay, so we're going to use C that gives us this common link between A and B, and we're going to use C as a bridge that gets us from here to something in terms of B. All right, so D is equal to A plus Y. So I'm just going to rewrite that as C minus x1 plus y. Okay, and I can do that because I knew that C is equal to A plus x1. I'm just solving that equation for A. All right, so then once I have that, I've got C minus x1 plus y. The parentheses don't really matter there. And then C is equal to B plus x2 minus x1 plus y. So now I have B plus this other thing here, kind of a mess, but everything there is an element of I. x2 is, x1 is, so the opposite of x1 is, and y is. So all of that is an element of I. So D belongs to B plus I. So what I've shown is that any element of A plus I has to belong to B plus I. So therefore, A plus I is a subset of B plus I. And I'll spare you the other argument. It's pretty much the same reasoning. You start with something belonging to B plus I, you re-express B in terms of C, and then use that C to get over here into something in terms of A. Quite nice. All right, so by similar reasoning, B plus I is a subset of A plus I. So A plus I and B plus I are exactly the same cosets, assuming they have a common element. Okay, therefore, additive cosets of an ideal are either disjoint or exactly the same. Okay, the point of proving this theorem, and I want to make sure I'm really clear about this, that we're not doing this just for fun or just for mental calisthenics. We're doing this because we want to justify this picture that we have, this concept image of a ring being partitioned into cosets according to an ideal. So again, one of the cosets is just going to be the ideal itself. If you want a coset name for that, we could call that 0 plus I. Because if you can write something as 0 plus I, then that means that thing is really just an ideal element. The 0 doesn't really add anything. And then everything else is some other coset, some coset disjoint from the original ideal and disjoint from all of the other cosets. So the way that we're going to construct R mod I is we're going to treat each of those cosets as one ring element in our new ring. So now we have a ring with, I don't necessarily want to say fewer elements, that may not be exactly the case, but at least in a conceptual sense, it is a smaller ring. And as I say all this, I realize we're starved for an example, so let's do one quick example, or at least introduce it so we have some idea of what's going on here. Okay, so let's take Z as our starting ring, and in one of the previous videos we established that the ideal of even integers is, well, an ideal, okay? So we can start building cosets of it. So for example, we can have 0 plus I, so that's the set of all integers of the form 0 plus x, where x belongs to the ideal. And well, x can be any even integer, so that's going to be 0, 2, 4, 6, that's a 0 there, and so on. And also includes negative even integers, so like negative 2, negative 4, negative 6. So that's one coset. And then for another coset, I might select some number not in this set. So let's try 1 plus I. And that gives me the set containing anything of the form 1 plus an even integer. So that would give me 1, 3, 5, 7, 9, etc. And also negative integers like negative 1, negative 3, negative 5, and so on. So that gives me, it looks like all of the odd integers. So I have here, it appears, all of the even integers. It looks like this will contain all of the odd integers, and we can verify both of those claims if we want to. And that means that at this point, I'm pretty much done. I mean, I could construct another coset like 2 plus I or 3 plus I, but each of those would be identical to one of these. So these two cosets form a perfectly nice partition of the integers. So let's draw a cartoon there. So this is the ring of integers, and here I have just the ideal, that is the even integers, and over here I have 1 plus the ideal, which contains all of the odd integers. And that is a picture of the quotient ring, Z mod I. It is a ring containing exactly two elements, I and 1 plus I. And anytime you think of a ring that contains just two elements, you should be tempted to say, hey, wait a minute, that's just Z mod 2. And in fact, that is true. That needs proof. But we can prove that after we talk about how we define operations for a quotient ring.